Shri Gurubhyo Namaha, children. Good morning, all. Yesterday, we were discussing about drift velocity. I was talking about the movement of electrons in the presence of an electric field, in the absence of an electric field. So, yesterday, we were discussing about drift velocity. So, whenever an electric field is given, what happens to the electrons? So, this is what we were discussing yesterday. Right, in the absence of an electric field, the average thermal velocity of the electrons was found to be Vi is equal to V1 plus V2 plus V3 up to Vn divided by N. Actually, the electrons, they collide with the positive ions and they gain thermal velocity, which is given by this value. When you apply an electric field, when you give an electric field, suppose you connect a metallic conductor to a battery, which is an external source of power supply. Now, as soon as this is connected to a battery, there will be an electric field that is created. Now, this electric field will attract the electrons. So, what happens as soon as this electric field is set up in the conductor? Now, the electrons will experience a force which is given by F is equal to E into E. Now, this is with respect to this formula, E is equal to F by Q, or F is equal to E into Q. Now, this Q is replaced by the charge of the electron. So, F is equal to E into E. So, we know the formula for force, which is M into A, and A is given by F by M. Now, for F, we will substitute the value of E into E by M, and thereby you get the equation for acceleration, which means whenever you give an electric field, the electrons get accelerated because already they have a thermal velocity. Apart from that, when an external electric field is given, it gets accelerated. And after acceleration also, they start moving and hitting the positive ions. Okay, ma? Right. So, what will be the final velocities of the electron? So, this is what we wrote yesterday. Final velocity of the electron, E is equal to the initial velocity plus acceleration into time. This is with respect to the equation of motion. This is the first equation of motion. V is equal to U plus AT. V is the final velocity, U is the initial velocity, A is the acceleration, and T is the time interval. So, with respect to individual electrons, we wrote V1 plus A tau 1, V2 plus A tau 2. Okay, and when we calculated the average velocities of the electron, these average velocities of the electrons are nothing but drift velocity. Now, as soon as an electric field is created, the electrons will start drifting towards the positive terminal. Am I making you the concept clear, children? Right. Now, this is where we stopped. I just redo this again. Okay, because I just directly arrived at the formula here. But how I arrived at the formula, we will discuss now. Okay, so let us go to the next page. We write the drift velocity Vd is equal to V1 plus A tau 1 plus V2 plus A tau 2 up to, if there are n number of electrons, so we have Vn plus A tau n divided by n. Okay, so when I segregate all the thermal velocities, V1 plus V2 up to Vn by n plus A into tau 1 plus tau 2 up to tau n divided by n. And we all know that this thermal velocity, which is this equation, see here, Vi is equal to V1 plus V2 plus V3 up to Vn by n. Now this is equal to 0, right? So here this term becomes 0. So I end up stating Vd is equal to A into tau. Okay, and I know the value of acceleration. What is the value of acceleration? Acceleration is equal to minus E into E by m. So when I substitute, here is the equation for drift velocity, which is given as Vd is equal to minus E into E by m into tau. Velocity is acceleration into time. So what is this tau? Now this tau is nothing but the average time between two successive collision of the electrons. Two successive collisions. Now this is also called as relaxation time. Relaxation time. Now this is a very important word, children. As far as this topic is concerned, this relaxation time plays a very important role. Suppose you consider this to be a positive ion. Okay, look at my face. This is considered to be a positive ion. Now an electron, here is the electron. Now this electron will come and hit. Okay, then again they go. Then they go somewhere again, once again they come and hit this positive ion. So what is the time interval between two successive collisions of the electron? It is taken as relaxation time, because once the electron comes and hit, they gain velocity. After that they go somewhere and once again they come back. So in between they have, when they are not colliding, that is the relaxation time for them. Okay, so average time between, now this is the first collision, again they go back and come back, this is the second collision. So the time interval between two successive collisions of an electron is nothing but you call it as relaxation time. So when you take the average of the time, it is replaced as tau. Is it clear, children? So this is the drift velocity of electrons in the presence of an electric field. Am I making you the concept clear, children? Yes. Now we are going on to the next topic. Again, it is continued in your textbook, children. I am going to find out a relation between current I, okay, and Vd, relation between current and drift velocity. Now look at this diagram again. It is a metallic conductor. Now I have applied an electric field. Now it is connected to a battery that is not shown here, children. So electric field in this direction, that is from right to left. Okay. Now when electric field is applied, the electrons which are in the right, they start moving towards the left. And what is the length of the conductor? Length of the conductor or the distance is Vd into T. Okay. Is it clear? So velocity is distance by time. What is the velocity formula? Velocity is distance by time. So what is distance? Distance is velocity into time. This is the formula I have taken here. So what is the distance, which is the length of the conductor? Okay, ma? So it is Vd into del T. Okay. Now let us consider an area. Now this area is perpendicular to E. Okay, area is perpendicular, area vector is parallel. Okay, I am talking about a small area. Let us consider this small area. Now this small area is perpendicular to E. Okay, now this is located inside a conductor, right? Now at a small infinitesimal time, for a small time, what happens here is all the electrons. Now when an external electric field is applied, for a small interval of time, all the electrons that are in the right side, they start drifting to the positive terminal of the battery. Now as far as this diagram is concerned, here will be the positive terminal, here will be the negative terminal, because electric field is in this direction. So all the electrons which are in the left side, they start drifting towards the positive terminal, which is at the right. So I'm going to start the relation between current and drift velocity. So how many number of electrons are there? Number of electrons per unit volume. Per unit volume is nothing but you call it as N. So what is this N? N is nothing but you call it as number density. So what is small n, children? Small n is nothing but number density, which is the number of electrons per unit per volume. So what will be the total number of electrons? So total number of electrons is equal to, you have n into V. V is nothing but volume of the conductor. So what is V? V is volume of the conductor. So how many number of electrons will be there is the number density into the volume of the conductor. But I know the volume of the conductor to be what? What is the formula for volume, children? Volume is area into length. Just make a note of all these things. All are very small formula. You have to just relate this to this. So V into L. L is nothing but the length of the conductor. For L, I will substitute Vd into del T. So total number of electrons will be, this is equal to N into A into L, which is equal to N into A into, instead of L, I will substitute Vd del T. Okay, ma? So what is the, now I have written the value of total number of electrons. So total number of electrons is this. So what is the charge? So let me write charge on total number of electrons. So charge on total number of electrons is charge of an electron into the total number of electrons. So it is Na Vd into T. So this is the charge, okay, which is represented as Q, right? So Q is equal to E into N into A Vd into T. So E is the charge of the electron, N is the number density, area of the conductor, drift velocity and time interval. Okay, so according to our formula for current, now total charge on number of electrons is Q. Now this Q is nothing but what? Current, right? Yes or no? What is the formula for current? Current is equal to Q by T, right? Rate of flow of charges. So this charge is nothing but, I can write it as current. Now since I have taken a small interval of time, so instead of T, I have substituted del T. So this charge is replaced by I into T. Okay, ma? So I will substitute Q instead of Q. I will substitute I into del T, which is equal to E into N into A Vd del T. Okay. Now what is drift velocity formula? Drift velocity formula we have substituted. What is drift velocity formula? It is E into E by M into tau. Okay, clear? Now I am going to substitute here. So I into del T is equal to, let me substitute E into N into A. Substitute for Vd as E into E by M into tau into del T. Okay, so here I am cancelling del T. So here is the value of current. I is equal to, now there is one E here and one E here. So let me write this as E square A by M. Okay, I take this N to this side, so it becomes N tau. Okay, into electric field. So this is the value of current. Okay, now I have to find out one more equation for this. Now we already know the value of current density. Remember last topic we read about current density. Current density J is equal to current flowing normally to an area. J is equal to I into A. Now in this case I is equal to, can I write J into A? Yes or no? Now compare this with this term. Now I have left side I. Now A is also there. Children, this is A. So this is A and the remaining term then will be J. Okay, so I can write I is equal to J into A, where J takes the value of, what is the value of J here? It is E square N tau E by M. So I'm just relating everything. See, nothing complicated here. I'm just relating everything. So J is equal to E square N tau E by M. Okay. Now in the previous topics, that is in page number, what is this page number? 97 of your textbook. Again there is a formula for J. J is equal to, let me write here, J is equal to sigma into E. Now compare, I have an equation for J as, let me write the equation for J here. J is equal to, what is the equation I wrote? E square N sigma by M into E, and I wrote the formula for J as, before this, let me strike off this. I will write I is equal to A into this term E square N tau by M into E. Now this is going to be the formula for, again I will write here J is equal to I by A, or I is equal to J into A. So here this will be the value of J, which is the current density. So I can replace this equation as I is equal to J into A. Okay, right? Now there is one more relation which talks about current density and electric field. J is equal to sigma into A. Now this equation is there in your textbook, children. The previous page 97 we discussed the relation between current density and electric field. We arrived at an equation J is equal to sigma into E. Okay, now I can also write this equation as J is equal to sigma into E. So when I write this equation once again, J is equal to E square N tau by M into E. So what will be the value of sigma now? The value of sigma will be E square N tau by M. Okay, so I can bring this to J is equal to sigma E also. So these are all. Now what am I doing is, it's a very simple derivation of how the metals behave when an external electric field. Now this is almost, I'm relating everything with Ohm's law. Whatever we discussed on Ohm's law, I have just reframed it in terms of other values, that's all. Okay, so this is with respect to the relation between current density and relation between current and drift velocity. Actually the relation between current and drift velocity is here. I is equal to NEA VD. Now when I cancel this term, now here is the relation between current and drift velocity. I is equal to NEAVD. Actually this is a very important relation where you have so many problems to do. I is equal to NEAVD. Now this is the relation between current and drift velocity, and we have also related so many concepts, current density and current, and we have also related current density with conductivity, which is also called as sigma. So what is the relation between current density and electric field means this is the relation where I can take the value of sigma to be this, which is E square n. Now these formulas are used to solve some of the problems, children. Okay, so that is why I ask you. Now all these formulas are there in your textbook, but they are given in a paragraph. That is why in order to make you understand, I just wrote like this. Make a note of this. Find out all the values. What is value of n? What is E? What is A? Everything you should know. What is tau? What is capital E? What is M? Depending upon the data given in the problem, you should use these formulas to get the answer. Okay. Next, we are moving on to a very small topic called mobility. Again, this is also related to Ohm's law. Mobility. Now, when you define mobility, mobility is nothing but mobility. It is represented by a symbol like this, mu. Okay, so mobility is nothing but drift velocity. It is defined as mobility is defined as the drift velocity per unit electric field. Per unit EF is electric field. Okay, so I'll write the formula for drift velocity. Mu is equal to drift velocity per unit electric field, E. Right? Now we know the formula. Okay. Now before that, let me write the unit. VD unit another. What is the drift velocity unit? Velocity is nothing but meter per second. And we also know the formula for electric field, which is volt per meter, V by D. Okay, so when I rearrange this, it is meter square into volt second. Actually, this is considered to be very large. So instead of meter, we go for centimeter square by Vs. Actually, this is the unit for mobility. Now let us substitute the value. So mu is equal to, now it is Vd by E. Now Vd value is, of course I know. What is Vd value? Vd is E into E by M into tau. Substitute here. So when I substitute E into E tau by M into, now electric field. Okay. Yes or no? So again E and E cancel. So here is the formula for drift velocity based on the acceleration. So it is drift velocity. So mu is equal to E tau by M is the formula for mobility. So it is nothing but it is defined as drift velocity per unit electric field. So your homework for today is, now start from page number 97. Page number 97, drift of electrons and the origin of resistivity. From there you will start, you will complete till mobility. All the derivation part, I want you to do it. Okay. So with this we are moving on to the next concept where we talk about the graphical representations, like limitations of Ohm's law. So where these Ohm's law is not applicable. Okay, now it is used in very vast areas, but there are some devices where the proportionality of Ohm's law is based on the proportionality of V and I. So there are some factors or some cases where this V and I does not hold good. Okay, so what are the deviations means? In some cases, now this is the first case, V ceases to be proportional to I. Now actually we talk about conductors as two types. One is ohmic conductors, the other one is non-ohmic conductors. So ohmic conductors are those conductors which strictly obey Ohm's law. In that case, the graph will be just a straight line. Straight line in the sense when you plot I along the x-axis, let this is the origin, and V along the y-axis. When we draw a graph, when we plot the points, ohmic conductors, they restrict, they just obey Ohm's law, and you will have a graph like this. So ohmic conductors. Non-ohmic conductors are those conductors which do not obey Ohm's law. Now as far as this diagram is concerned, now for smaller currents, whenever we talk about when you allow very small current to flow through in a metallic conductor, for smaller conductors, the VI graph will be a straight line. This is how the graph looks. It will be a straight line. Now, when you vary the potential, current also will vary linearly, okay, for smaller values of current. But when you allow a large current to pass through the circuit, what happens is the resistance of the metallic conductor raises, it increases, because you are allowing more current. And what happens to the graph is you cannot call it as no more linear. Now there is a small variation here. See this, see this. Now this is applicable only to larger value of currents. Okay, look at there are two lines here. They have given the dashed line represents the linear Ohm's law. The solid line is the voltage versus current for a good conductor. That is, when at higher values of current, the graph is not linear, but there is a turn here. Look at the diagram. You should be able to explain. You should be able to understand this. So for the larger value of current, conductor becomes non-ohmic. Okay. Now the next graph is, this is also the diagram where the Ohm's law is not applicable. Here this is with respect to a PN junction diode. Hope you remember this. This we have done already in the second volume, semiconductor physics. Here also in the forward bias, look at this. This is a forward bias graph. For smaller values of voltages, current will be small, and after that you will have a steady value of current. Now in the reverse bias, there is no current. So PN junction diode, as far as it is concerned, it does not obey Ohm's law, and the current is allowed to flow through in only one direction. And we have also read, since the current flow is in one direction, this PN junction diodes are used as rectifiers. So here also we do not obey Ohm's law. And this is the third condition. This is the behavior of gallium arsenide. Now here also it is a non-linear behavior. Okay. Now here after a certain voltage, now here look at this graph. Here it is increasing, but after some time the current is decreasing. Okay, so you have the resistance value to be negative as far as this graph is concerned. Now as far as this part is concerned, current is increasing, whereas this part is concerned, the current is decreasing. So these are some of the areas where we will not strictly does not obey Ohm's law. So go through the graphical representations in your textbook, have a very clear understanding. We'll be continuing with effect of resistance in the next class, children. Okay ma, see you.